Okay, so today is just a review lecture. Seeing as there's only three of us here at the moment anyway, this can certainly be more of a discussion, and I can also skip over bits, or we can discuss other aspects of the course if you prefer, rather than me necessarily working through this like particular example. I just wanted to highlight again that I'm running this special topics course on maths of evolution, and this course here is a very good prep for that. So if you're interested in that, please, you can always drop me an email or put a reminder in if you want to look at it for the summer. I'll also probably be advertising the USRA project, or I am advertising already actually, modeling microbial evolution. Yes.
Are there any other prereqs for 495?
No, to be honest, this course probably won't even be an actual prereq. In much the same way that I had originally set up, say, 155 to be a prereq for this course, and then actually changed it because most of the people that did 155 couldn't take this class because of a clash. So I had to change the prereqs to this and take that out. So for the kind of the same reasons, and also because this is the first time this course is run, I won't put 360 as a prereq. However, that being said, because of that, we'll have to recap a certain amount of material from 360 in order to do this. So if you've taken this class, you'll probably find this easier than everyone else will, because there'll be, have to spend a bit of time introducing a competition model, introducing an infectious disease model. The stuff we've just been doing on evolutionary epidemiology, we'll be going into that into more detail, but you've already been introduced to it. So that's why I say it's very good prep, because there'll be a certain degree of overlap with this, but it won't be a prereq. Yeah, Scott did a USRA with me, hopefully not completely scarred. So if you're interested to ask Scott for completely I'm not going to ask you to say how it went now, because that seems a little bit unfair. Okay, so what I would thought we would go through today is an example of an SEI model with demography. So this is just a variation here on the types of models that we've looked at before. We're dealing with proportions again, so it's already been rescaled according to population size here. And the basic idea of this population, or this infectious disease, we can draw a schematic of this. We've got these three classes, S, E, and I. Individuals become infected, but they're exposed, so they're not yet infectious, at a rate beta SI, so per capita rate beta I. And then they go from the exposed to the infectious class, so infected and infectious, at a per capita rate sigma. And then we have per capita death rates for each class given by D, where D is a natural or background mortality rate, so everything else but our infectious disease. And then for our I class, our infectious class, so we kind of think of this as almost this exposed class as being pre-symptomatic, and then here they have symptoms. Okay, so here they only have this additional disease-associated mortality when they reach their infectious class. So you can think of this as being pre-symptomatic and then actually symptomatic. And then finally, we have also some births, and everyone is born susceptible. So note that there's no recovery in this model. So you can think of this as being like a chronic infection, or infection where people are not able to clear it. So they, for example, some people that are immunocompromised can get infected by things that we would be okay with, but then they're unable to clear that infection, so they would just end up permanently in this I class here. Okay, part of the reason for doing that is just because it makes also the modeling a little bit simpler, and because we're dealing with proportions here, these are all going to sum to be equal to 1. Okay, so the first thing I wanted to recap is going over the next generation matrix method to find R0. We went through this a little bit. I believe this was actually when I wasn't here doing the host heterogeneity side of things, but I thought I'd recap it in the context of this model here. Okay, so we want to calculate R0. And if you remember, R0 is all about telling us the number of new infections produced by a single infected individual when everyone else is susceptible. Okay, so thinking about the dynamics really early on, and if this R0 is greater than 1, that means that our infection is expanding in the population, and if it's less than 1, it's declining. Okay, so is an epidemic going to take off or not? Okay, so given that we've got we're dealing with proportions, we're thinking about the case when our S class is approximately equal to 1. So almost everyone is susceptible. And then let's think about the dynamics of our infected classes. So here there are two of these. We've got d dt is now going to be approximately equal to, it was beta si before, but s is approximately equal to 1. So this is just going to be beta I. And then the rest of that equation is the same as before. So we have minus sigma minus d, that's by e. And then our I equation, well, this doesn't change at all. So we still have sigma e minus alpha plus d, that's by I. So typically if we don't have an exposed class, what we usually do is we look at the per capita growth rate of this I class here. So you'd look at 1 over I di dt and see when is this positive, and then solve that inequality. So you end up with 1 on, you'd have R naught is greater than 1. So from this, you solve it, so you end up with an expression that looks like that, R naught is greater than 1, okay? That's what we would usually do. You can't do that here because we have to take into account this exposed class here. Reason being that some infected individuals go into this exposed class, but then they're lost due to natural mortality. If you don't have this natural mortality here, you can add these two classes together and there's no loss from here, so it doesn't affect your R naught at all. We'll show why that's the case in a moment. But because we do have background mortality here, we have to use this next generation method to find our basic reproduction number. So we need to look at our Jacobian matrix first of all. And what we're really doing is this is just a variation essentially on our stability analysis. So remember, our R naught is telling us when can an infection spread into an otherwise susceptible population. So what we're really saying is we're analyzing the stability of our disease-free equilibrium. So we're asking, when is that disease-free equilibrium unstable? If it's unstable, then our infection is going to grow. And if our disease-free equilibrium is stable, then our infection is going to die out. And we just go back to our disease-free equilibrium. Okay, so that's what we're really asking here. And that's why we end up looking at our Jacobian, because we're going to be looking at the stability of that disease-free equilibrium. So we're going to look at our Jacobian of just our infected classes, because we don't care what's happening with our S class. We can also, we don't care what's happening with the S class because we're dealing with our S class being approximately equal to 1, so it's essentially fixed here. So that means we also only need to look at a 2x2 Jacobian. Okay, so we can work out the Jacobian of our system and our disease-free equilibrium. So I'm going to write, this is with respect to E first, so the first equation, d dt, we're going to have a minus sigma plus d. With respect to I, we're just going to have a beta in this term here. For our second row, di dt, we're going to have, oh, I tell you what, I think I might have forgotten to share my screen on Zoom. Bear with me 2 seconds. I did. This wasn't being recorded. Okay. This is why you should show up to your lecture, just in case there are technical issues. I'm glad I remembered that. Anyway, so we've got our Jacobian here. We've just worked out our partial derivatives for d dt, and then for our second equation, di dt, we're just going to have a sigma in the bottom left, and then a minus alpha plus d in the bottom right. Can't believe I got all the way to the last lecture without making that mistake. I thought I was definitely going to forget to share my screen earlier than that, and this is the first time it's happened. Okay, so this is our Jacobian. Why do we care about our Jacobian? Well, our Jacobian, the eigenvalues of our Jacobian tell us about the stability of the equilibrium. And remember, this is the disease-free equilibrium. If we did our, I've already essentially put it in here, we would have had an S star here, because this would have been a beta Si. So we would have had an S star here, but I've already substituted in the fact that S is equal to 1. Okay, so that's where that S star has disappeared to. Okay, so if we find that the eigenvalues of this Jacobian at our disease-free equilibrium, which already is at our disease-free equilibrium. In fact, I'm going to write at our DFE, we have this. Okay, just to make sure that's clear. If the real part of our eigenvalues is positive, in fact, there will be real in this case always. So if our eigenvalue is positive, our largest eigenvalue is positive, then that means that what? For our disease-free equilibrium. If the largest eigenvalue of this is positive, that means it's going to be unstable. If our eigenvalues of this are both negative, both have negative real parts, then our disease-free equilibrium is going to be stable because any perturbation, remember this is telling us about our perturbation. So what we've really got is we've got our SEI is going to be equal to, say, just for argument's sake, 0.999, 0.0005. I think I've got my zeros there correct. Okay, so we've moved a tiny little bit away from our disease-free equilibrium. Almost everyone is susceptible. Got a tiny little bit of exposed and infectious individuals. Is that going to decay back to 100? Or is it going to go away and grow? Often the susceptibles are going to be depleted and we have an epidemic. Okay, so what we're saying then is those second two classes there, we want to know whether that little perturbation is going to grow or decay when we're at a disease-free equilibrium. It's going to grow if our largest eigenvalue is positive. And if both eigenvalues are negative, then it's going to decay. So from that, that therefore tells us, R naught is telling us whether our epidemic is going to take off or decay. So it's exactly the same as working out whether these eigenvalues are positive or negative. However, that's a little bit of a pain because in this scenario here, we have to find our eigenvalues, we have to solve our characteristic equation. So that's determinant of our Jacobian minus lambda times by I, where lambdas are our eigenvalues, equal to 0. I mean, it's only a quadratic, but it's still a little bit of a pain. In principle as well, there's two classes here, but we could have a model with many classes. You could have, say, this structured by risk or age. They could be structured by sex as well. So, there could be many, many components here, and solving this could be difficult. You might be solving a quartic or something even higher order. So we can use the next generation matrix instead, which essentially transforms this problem by doing some clever math. And we've not gone into the details as to why this works. You just kind of have to take it on faith that it does work. But it shifts the problem so that we find some eigenvalues of a new matrix, and those are typically much easier to find than this one here, where we'd have to solve this characteristic equation. So that's why we use this method. So to use this method, what we need to do is we need to split this Jacobian into two separate matrices called F and V. And these aren't just two, obviously there's an infinite number of ways in which you could do this. There are specific rules around what goes into F and what goes into V. Okay, so our F matrix, this contains all terms in the Jacobian that correspond to new infections. Incidentally, we can also use this you actually end up using the same method for calculating invasion fitness if you have a model with multiple classes as well. So that is it's a bit of a tangent, but like the same method actually applies much more broadly as well. In that sense, here we're talking about new infections because those are essentially births of new pathogens. So if it was in a different context and you were making a next generation matrix to work out invasion fitness for a host population with different levels of resistance, say, it would be new births of those hosts, okay? The key thing is it's births here or new infections. So in our original matrix, where are our new infections coming in? Like which terms within this Jacobian correspond to new infections? It's not a trick question, don't worry. So sigma is individual. So, okay, if I think of the E class as being, so you're exposed and you're, say, asymptomatic, but you're not infectious yet, and your I class is people who are sick and infectious. If you were to take a COVID test and it was positive, would you, but you don't have any symptoms yet, would you class yourself as being an infection that's just happened, as opposed to when your symptoms become onset, right? So the new infections here are just this beta here. So when they move from the E class to the I class, that's not a new infection. They're just changing their symptoms. Say, okay, they're still the new infections are only the ones that go into this exposed class. Okay, so that means that we only have a beta in this top right term here. Everything else is equal to 0. And because of this relationship here, J is equal to F minus V, V is then going to be just minus all the other components within that Jacobian. So we have a sigma plus D. The beta has disappeared, so we have nothing in the top right. We have a minus sigma in the bottom left, and then a alpha plus D in the bottom right. So this V matrix then is everything else that isn't new infections. So that's a transition between classes and loss from those classes as well. Another way, if you're not sure about what classes as new infections, is to think about what happens if we could break this model down. You know, this is a simplification saying this is everyone who's infected, regardless of how long they've been infected, right? You could break this down into having an I1 class, so those who've been infected for 1 day, 2 days, 3 days, 4 days, and so on, right? You would still only count the new infections as the ones that go into this first class, not transitions between these classes, okay? You wouldn't say each of these is a new infection, it's just the ones going right to the beginning, okay? So we've got our two matrices now, F and V. So now we can work out our next generation matrix. And this next generation matrix is just given by our matrix F times the inverse of V. So we do need to find the inverse of a matrix. That can be a little bit tricky, but usually it's easier than, yes.
Just some quick questions.
Yes.
On the previous two slides.
Yes.
To clarify something. So when you have the Jacobian is at the DFB already, is that because you're assuming that the initial population is also susceptible? Or?
Yes, exactly. So we're by definition, our R naught is defined by our disease-free equilibrium, right? So if I calculated my general Jacobian would look like this. And that Jacobian would apply this, it would be the same Jacobian here with this beta S star at, say, the endemic equilibrium, right? And then to work out the stability of your endemic equilibrium, you would substitute in S star here. We would also have to, at that point, factor in the fact that we've got a dSdt equation that we've not incorporated into this. So there would be additional things going on here. The reason that I've just cut that S star out here is because I'm just evaluating at the disease-free equilibrium to start with. Does that make sense? Yeah. So R naught is defined by that disease-free equilibrium, which is why we're focusing on that.
And then when thinking about this, like when it's unstable, it's the largest eigenvalue being positive. Mm-hmm. Why do you not care about that other eigenvalue?
Because all we're asking is, we've got two possibilities here, right? Either the disease takes off or it decays and goes to 0. So if at least one of those eigenvalues of this matrix is positive, then it's going to be moving away from your disease-free equilibrium, and so it's going to be taking off. So it could be, this could be a saddle. So one could be positive and one could be negative. And that means that in some directions you will move towards your disease-free equilibrium. Say if one of these classes was equal to 0, you might move towards your disease-free equilibrium. In fact, that should be the case, right? If your I class was equal to 0, Oh, I guess no, you would take off that. There's possibilities there that if you had a very long latent period and you had no infectious individuals and they were only exposed, that it could decay towards zero before it would take off, right? So this might be a saddle. So one might be positive, one might be negative for your eigenvalues here. All that matters is that you've got some direction that you can move away from that disease-free equilibrium. So it doesn't matter if you get pulled into it in some directions, as long as there's one way that you can get pulled away, that means you're going to have the epidemic taking off. And so there is an R0 greater than 1. And if they're both negative, then you always just decay towards, if you have a stable node at your disease-free equilibrium. Does that make sense? Okay, good questions. Okay, so our next generation matrix, given by F times by inverse of V. So 2 by 2 matrix, inverse of V is going to be, in fact, I'm going to pull out a factor, divide by the determinant at the front. So the determinant of V is just going to be the product of the elements on the main diagonal. So sigma plus D times by alpha plus D is going to be our determinant. So we do 1 over the determinant times by the rest of the elements. If you remember what we do to find, let's call it here, if we've got a matrix X is equal to A, B, C, D, then X inverse is going to be equal to 1 over the determinant of X. So that's AD minus BC, assuming that that is non-zero. And then here you switch the elements on the main diagonal around, and then you would take minus the elements on the off diagonal. So following that same formula here, this is just a generic thing. Ignore the fact that there are D's in both of these. This is just a generic 2 by 2 determinant, and then 2 by 2 inverse. So here, switch the elements, the order of the elements on the main diagonal. So we can have an alpha plus D in the top left, a sigma plus D in the bottom right. 0, this remains a 0 in the top right. We had a minus sigma there before, and this is now going to just be a plus sigma. Okay, so that's my inverse. And then to work out our next generation matrix, that's F times by V inverse. So I'm going to keep this factor at the front. My F matrix was 0, beta, 0, 0. And the rest of my inverse, we had an alpha plus D, 0, sigma, and sigma plus D. So the nice thing about this, you notice, is that we've got lots of zeros in this. And this is typically what happens when you have your F matrix. Typically your births are coming into, say, just one class. That usually means that we have lots of zeros in this F matrix. So that means that when we multiply these things together, in this case here, our top left element, we're going to have 0 times by alpha plus D, and then we're going to have beta times by sigma. So this is just going to be beta times by sigma, and then divide by the factor on the outside. So sigma plus D times by alpha plus D. The element in the top right, we have 0 times by 0 plus beta times by sigma plus D. So we'd have a beta times by sigma plus D, but we've got a sigma plus D that we're going to divide by over here. So we're just going to have beta over alpha plus D. And then the second row, because of these zeros here, the second row is just going to be zeros. Okay, so that's just matrix multiplication. And then now in this new next generation matrix, our R0 is equal to the largest eigenvalue of this matrix. And because this is a diagonal matrix, our eigenvalues are 0 and this element in the top left. So we can read it straight off. We don't have to solve the characteristic equation in this case. And often doing it using this method is a bit simpler. So this is now our R0. Beta sigma over sigma plus D times by alpha plus D. Okay, just an important distinction here. When we're finding our R0 directly from the eigenvalues of the Jacobian, which I'll leave that as an exercise if you want. Find the eigenvalues of this and then see when they're positive. And then from that, work out your R naught. But remember, your R naught is always determined by this threshold of being greater than 1 or less than 1, right? So you need to get essentially rearrange your eigenvalues so that you get R naught is equal to something which is greater than 1. Okay. But your Jacobian here, you find your eigenvalues of this Jacobian, say, to find your R naught, and then you work out when those eigenvalues are positive and then rearrange it in such a way that you get an expression greater than 1. When you're doing your next generation matrix, essentially it shifts the problem over and your threshold for stability is no longer at 0, it's at 1, which is nice because we all care about R naught being positive, being greater than 1 or less than 1. Okay, so here we can just read it off straight away. The eigenvalue here is our R naught. The eigenvalues of the largest eigenvalue of this is not R naught, but it allows you to find R naught by shifting the threshold to 1. Does that make some sense? Okay, so it's important that it shifted the stability threshold. Okay. Okay, let's think a little bit about interpretation then. So what effect is the latent period? So this is 1 over sigma. This is how long on average individuals spend in the exposed class. What effect does that have on R naught? Okay, so first let's think about what happens if there's no background mortality. So in this equation here, if there's no background mortality, our R naught is going to equal beta sigma over sigma times by alpha, which is just beta over alpha. So in this case here, there's no effect of our exposed class at all on R naught if there's no background mortality. And this is what I said earlier on, that the exposed class only has an effect if we're losing individuals from that class who don't become infectious. It will affect the time of things, right? If there's a really long latent period, it will affect the rate at which the epidemic occurs. If it's taking weeks or months for your latent period as opposed to a day, then your epidemic is going to progress much slower. But it doesn't affect whether it happens or not. It's just going to affect the speed of it. And this R naught doesn't tell you anything on its own about the speed at which things happen. This is just a number, so there's no time component to this. Okay. So no background mortality means no effect of the latent period on R naught, because no individuals are lost. So let's think about the case where there is background mortality, and think about what effect this latent period has. So if the latent period is very long, in other words, 1 over sigma is very, very large, or sigma itself is very, very small, close to 0. We think about what happens as sigma tends towards 0. And R naught is going to tend towards beta times by 0 over d, or rather 0 plus d, to make sure it's clear what I'm doing here, times by alpha plus d, which is just equal to 0. So if there is background mortality, we have a very, very long latent period, our R naught is going to tend towards 0. That should make some sense, right? If you have an extremely long latent period so that they never become infectious, you're never going to be creating new infections. So R naught will tend towards 0. Let's think about the opposite then. What happens if our latent period is very, very fast? In other words, sigma tends towards infinity. So 1 over sigma is going to tend towards 0. So on average, you spend a very, very short period in our exposed class. Well, here we can take our R naught. In fact, I'll write it up here. If you want to work out limits, one of the things we can do is we're going to be taking the limit with respect to sigma here. So if we do the same on our numerator and denominator, everything stays the same, right? So if I divide the top by sigma, and then divide everything on the denominator by sigma, we're going to have 1 plus d over sigma times by alpha plus d. Okay? This is exactly the same. These two things are identical, right? Just one of them here, I've got a sigma here, and one of them I've divided by sigma. Make sure if you do this, you don't divide both of these terms by sigma. Okay, you need to, it's like having a 1 over sigma here, and you multiply that by one of these brackets, not by both of them. Otherwise, you're dividing by sigma squared. Okay, so what's my R naught is going to equal this. That's true in general. And then what happens as sigma tends towards infinity? Well, this term here, this coefficient is going to tend towards 1, because d over sigma is going to tend towards 0. So R naught is going to tend towards beta over alpha plus d. And this is what we would get in our, we just go all the way back to the beginning. If we didn't have this exposed class here, right? If we just had beta si here, and we worked out our R naught in this case would be beta over alpha plus d. And so the two things match up, right? If we have a very, very short latent period, the model is well approximated by removing that latent period entirely. And we basically get our R naught in the limit of that just SI model. Okay, so one last thing we can think about is considering our gradient of R naught with respect to sigma. So if we just take our derivative, I'll take out a factor of beta over alpha plus d. And then here we're just going to have to use the quotient rule. So in the interest of time, I'll just write down the answer. So you'd have a sigma plus d minus sigma over sigma plus d all squared. That's just from the quotient rule. Again, I'm not going to show the working, well, that is the working of it, but I'm not going to go through each bit in detail just for time's sake. The sigmas cancel. And so this thing here, why do we care about this? Well, this is positive, okay? That means that as sigma increases, R naught increases as well. So if we were to sketch this, we would have something that looks like this. As sigma increases, we've got R naught. We know that when sigma is equal to 0, R naught is equal to 0. We know that as sigma tends towards infinity, we're going to tend towards beta over alpha plus d. So we're going to asymptote, and it will look something like this. Again, the fact that this derivative here is positive should make sense, because the faster our individuals are leaving the exposed class, the less time they're spending in the exposed class, the less likely they are to die from other causes before becoming infectious. Okay, so the reason I've gone through this example is just to help illustrate why we might want to use the next generation matrix, how it relates to stability analysis in general for disease-free equilibrium, and then thinking a bit about interpreting R naught if we want to, R naught is just a function of various parameters or variables if we're thinking about them varying. And we can think about what happens in the limits of those different parameters will tell us something about R naught. Okay, so we could do the same and think about what's the limit of R naught as, or what effects does beta have on R naught, or what effect does D have on R naught, or alpha have on R naught, using a similar method of maybe thinking about the gradient, or we can think about the limits as those parameters get very large or very small. Okay. Okay, there's not a lot of time, but I did want to, someone had asked to go through phase plane analysis. It's a good question. Are we going to have time to do this? What I will do actually instead is I can go through some phase plane analysis, but I also want to give you guys the opportunity to ask if you have any particular questions that you want from other material that you want me to address before doing any of that. Is there anything else from the course that you'd like me to recap? Good with everything. Yeah. Yeah, did you have something?
I want to ask about
Question. maybe we can discuss that afterwards then. Yeah, okay. Anything else? Okay, I'll go through this. Someone did ask in the survey I sent out to go through phase planes again, so I'll do it in the context of this model. It's a bit different to some of the things we've done before. It's mainly the same ideas. It's just we'll use a slightly different method. Okay, so we could solve. One thing we've not done with this model is we've not found our endemic equilibrium. We've not done the stability of that. We can do these things geometrically using phase planes. And we're going to do it without even finding what the endemic equilibrium is. Okay, so one thing we can notice with this model, because we have S plus E plus I is equal to 1, we can eliminate S from our equation because S is equal to 1 minus E minus I. So that means that we can write this as beta times by 1 minus E minus I times by I minus sigma plus D times by E, and the I dt is, as before, sigma E minus alpha plus D times by I. This is all going to be on the notes online, so I'm going to go through this reasonably quick. I won't wait for you guys to catch up with notes, just because I want to make sure I cover it all, okay? So don't worry about jotting everything down. Okay, so this is just a two-dimensional model, right? So we can put one, we can think about our null lines and sketch a phase plane just as we did before. So let's think about our null lines. Let's think about the dt being equal to 0. Well, we can write this as beta times by 1 minus I times by I minus sigma plus D plus beta I, all in brackets, times by E being equal to 0. In other words, we can rearrange this that E is equal to beta times by 1 minus I times by I over sigma plus D plus beta I. Okay, so this is my null line, or null lines, if it possible, must satisfy this equation here. And I'm going to call this f of I, because we've only got i's on this right-hand side. So this is just some function of our infectious class. And then our null lines for our I class, the I dt being equal to 0, well, this equation here is just linear in E and in I. So we can write E is equal to alpha plus D times by I over sigma. And I'll call this G of I. So this G of I here is just going to be a straight line. It's a straight line through the origin. And if we put E on our vertical axis and I on our horizontal axis, it's going to have gradient alpha plus D over sigma. So this is just a straight line. This thing here is a little bit more complicated, but we can see that if we set I is equal to 0, our denominator is non-zero, so that's good. But our numerator is going to equal 0. So when I is equal to 0, E is going to be equal to 0. When I is equal to 1, again, this is going to be equal to 0. This is non-zero. E is going to be equal to 0 again. So we have these two anchor points here. When I is equal to 0 or I is equal to 1, then E is equal to 0. That should make sense as well, right? Because we're talking about proportions, at least for when I is equal to 1, right? If everyone's infected, then they can't be exposed, right, by definition. But we also have, if no one is infected, we're going to have no one is exposed either as well on this null line. And we can also see that when I is between 0 and 1, this is going to be positive, and this is going to be positive, and this is all positive. So it has to increase. I'm not going to show that this has just one maximum. You can show that, but we'll skip over that stage for now. Okay, so we've got a few characteristics. This is going to look, it's not going to be like it's going to be some sort of curve with a peak between 0 and 1, and it's going to cross the horizontal axis at 0 and 1. Okay, so what about our direction field? In fact, what I'll do is I'm going to sketch some phase planes now. I'll sketch these null lines on now, and then we can add our direction field afterwards, okay? So I'm going to consider two types of phase planes, and the reason is because there's two orientations that we can think of for these null lines. So this is going to be my E on my horizontal, my vertical axis, and I on the horizontal. And then I'll keep the same notation. So my null cline for, let's do it differently, let's do it like this. My null cline for dE dt is going to look something like this. There's two cases. It crosses, this is dE dt is equal to 0, crosses the axes at 0 and 1. And then my null line for the I equation was just linear, if you remember. And there's two possibilities. There's one case where it starts off and it has a higher gradient like this. It's the only intersection happens at the origin. And the other possibility is that it intersects the curve somewhere for some positive values of E and I. Okay, these are the only two orientations you can have. In this left-hand example, there's one equilibrium, and in the right-hand example, there are two equilibria. So next thing we need to do is we need to find our direction field. If you recall, typically we would find our direction field on our null lines, and often we would use our axes, but there aren't null lines on the axes here. Note there's no null lines on the E and I axes. But whenever we're finding our direction field, the reason we use the null lines typically is because it's a little bit simpler, because you, by definition, you can only say be going up or down or left and right on those null lines. But you could choose any point in the space if you want to find your direction field. Okay, it's just often it's a little bit more complicated. So remember, if we're going to have E and I oriented like this, what happens if we are somewhere on our vertical axis? So I is equal to 0. And we're going to assume that E is positive, okay? So you're somewhere on that vertical axis, but you're not at the origin. Well, in that case, let's look at our two equations. Our dI dt, in this case now, we're going to have sigma times by E. Before, we would have had minus alpha plus d times by I, but that's just going to be equal to 0 because we're on that axis where I is equal to 0. So when we're on this axis, the I dt is going to be equal to sigma E, and we said that E is positive, so this is positive. And so that means that, according to our orientation above, we're going to have some net movement to the right. Okay? But we also need to think about our equation for dE dt. And here, dE dt would have been beta Si, but I is 0, so that term is going to be equal to 0. And then we had a minus sigma plus d times by E, which is always going to be negative. So that means we're going to go down. So on that axis, we're going to have a net movement going down and to the right. Then we do exactly the same for the other axis. So on E is equal to 0, and we're going to assume that we have I greater than 0, so that we're not stuck at the origin. Then let's think again about our original equations. dI dt is now going to equal, previously we had a sigma E here, but that sigma E is going to be 0 because E is equal to 0. And we just have a minus alpha plus d times by I. So that's always negative, so we're going to have net movement to the left. And dE dt, previously we had, or rather the equation is beta I times by 1 minus I. So beta I times by 1 minus I, that's our new infections. And then we had a term here, which was minus sigma plus d times by E. But if you recall, we're setting E to be equal to 0 because we're on that second axis. And this here is going to be positive. In fact, let's be a little bit more correct and say if I is between 0 and 1. So we're not at either 0 or 1. This is then always positive. And so our net movement has to be going up and to the left. Okay. So let's think about these two phase points. I'm going to do, let's see. I'll do them in the order they're in. Okay, so the one on the left, when we were on the line I is equal to 0, we've just found out that our net movement is down and to the left. So any point on this axis here, we would be moving down and to the left. And then on the horizontal axis, our net movement is going to be up and to the left. So on the horizontal axis, we're going to be up and to the left. In fact, in both of these orientations, that's true. So the arrows on the axes are the same. Now recall that we only change direction from going up to down or left to right when we pass through a corresponding null line, okay? So on this red null line corresponds to the IDT being equal to 0. So that means there's no movement left or right. So on this red line, I have to be moving either up or down in both of these diagrams. And on the green null line is when dE dt is equal to 0. So we can't be moving up or down, we have to be moving left or right. So we have to have horizontal arrows on our green null line. I've just drawn the lines in now because I haven't worked out what the arrows are. And then at this point, using that idea that we have to have continuity in these phase planes, if we start off over in this top left region here, we're moving down and to the left. We have to still be moving down when we pass through this null line. We can't have suddenly been moving up, right? Because this null line is dI dt being equal to 0. So on this side, dI dt is negative, and on this side, yes, this side, we're going to be changing direction. Sorry, I said that slightly the wrong way around. Here, we're moving to the right, is what I should have said in this region here. So dI dt is positive here. We're moving to the right. Here, it's equal to 0. So we're neither moving left nor right. And on this side, dI dt is going to be negative, so we move left. Okay? So that means that these arrows have to continue moving down here. Likewise, in this null line here, underneath this green curve, we're moving up and to the left. So our dI dt is going to be, our dE dt here is going to be positive because we're moving up. Our dE dt is positive in this region. Our dE dt is equal to 0 on the green null line, so we're neither moving up nor down. And then it has the opposite sign in this region here above the green thing. Okay? So here we're going to be moving down. So dE dt is going to be negative. It's equal to 0 here, and it's positive here. We're not changing whether we're moving left or right as we pass through this null line here. So we're moving left below, so we have to be moving left here. So that means that I can choose any point in this space. I'm conscious it's 20 past, so I'll keep going. Any point here, we get pulled in towards 0. Now, if you follow exactly the same logic as I've just done previously, you would be able to fill in the arrows accordingly on this side. In this orientation, so again, we're only changing direction when we pass through a null line. In this scenario here, we move, that shouldn't go that way, that should go this way. We move towards this endemic equilibrium here. Let's start here, for example. I move down, and then maybe like this. So in this case here, our disease-free equilibrium is stable because all our trajectories move towards it. And here, our endemic equilibrium is stable. And by convention, the right-hand side is when R0 is greater than 1, and this is when R0 is less than 1. So this is an example of how we can find the stability without having to actually find out what the endemic equilibrium is. It's how to sketch a phase plane by just choosing any point within this space, rather than necessarily being on a null line. So it's a slightly different way than what we've done before, but showing you that some of those techniques that we've learned can be a bit more generalized. You don't have to choose a point on a null line to find your direction field. You don't have to algebraically find out what your equilibrium is to find its stability. Okay, I realize I went through that one quite quickly. Only went through phase planes again just because someone asked me to. Very, very quickly, because I know that it's the end of the lecture. Just a few tips for the exam. Structure your answers clearly. I always say think about telling a story with a beginning, a middle, and an end. So the beginning, you're setting up your problem, like say what you're going to do, or just define your model or whatever the question's asking. Make sure it's clear what you're going to do. When I say that, it might only be a sentence, it might just be a couple of words, it might just be the equations, but make sure it's clear what you're starting with. Have a middle. This is where your analytic steps are showing you're working. Make sure it's just like a story. It can't jump around all over the place. It needs to have a logical order. It's much easier to follow and give partial marks as a logical order. Use linking words, therefore, or, this is the equilibrium and now this, try and link those sections together like I do when I go through these work examples. And then an end. Try and tie things together. If you found, say, 4 different equilibria, tie it all together at the end, and hence the equilibria are this, 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 and this. So it's clear what your conclusion is. So try and think of that idea of a story when you structure your answers. I'd say make sure the answers make biological sense. This is a math bio course, so no negative population sizes, no negative death rates and things like that. Make sure things make biological sense, and make sure your answers are not contradictory. So a classic one that people do is they'll say sketch a phase plane, and this case here on the right-hand side, this will be a stable node, say, on the phase plane, and then in the algebra, they'll say it's a saddle or something like that, right? Make sure that the 2 answers make sense and they don't contradict each other. And then also make sure these figures are clear and legible. I don't want to see figures on a page that are like tiny, and it's really hard to then give marks, okay? So no postage stamp sized. Thanks. Other than that, thank you. This is Herbie. I don't know if you remember seeing Herbie earlier in the course. My dog wishes you all the best with your future studies. Okay. I'll see you guys at the exam. I will hold, actually, yes, that another announcement. I will hold office hours from now by Zoom. So at the same times on the schedule, but the Friday one I won't hold in my office. I will hold it by Zoom. I think most people probably won't be coming to campus, so it'll be easier to do it by Zoom. Okay. All the best.